Next, we've got Colin coming up to speak to us about, what's he calling it? Measurement something. It's called ISP Interconnection, and its impact on internet performance. And you can use the clip-on, or you could use the podium. It's either way. It's just fine. Clickers on that.
I think the alternative to this is prying into other people's business. So just a word about where I'm coming from. I'm Colin Anderson. I am, amongst other things, an advisor and a researcher with Measurement Lab. As I've had conversations with people, I've realized that maybe the base knowledge on Measurement Lab is not what I think we'd hope to be. So to spend a small amount of time on it, Measurement Lab is one of the largest collaborative research platform, open data platforms. All of our data, all of our methodology are online, publicly available. In fact, our data is public domain. We host about 16 different tests. They measure a diversity of performance factors from bulk throughput to things like interference, traffic classification, traffic shaping, and even path data through things like reverse and Paris traceroute. We have about more than 80 sites. We cover about every one of, near the majority of Dine's Baker's dozen as far as transit providers. Most of our sites are located within transit providers rather than being at the edge of a network or with being in a CDN. And this is very intentional in the case of the research that we're going to talk about now. If you do know about us, one thing that you'd want to know is that, a couple of things that you'd want to know is that we've rapidly expanded in the past year. We have more coverage in a lot of the US transit providers. We've named a few, I left off a couple. We've rapidly expanded the number of sites, so that's going to factor into a lot of the things that I'm going to talk about today. But we also have a larger international presence. We've expanded into Canada, we've expanded into Africa, we've expanded into Asia, and so this means effectively more granular data for interesting research questions that are not just specific to the United States or Europe, but globally. I can't stress the openness enough. This is a network and a data source built for network researchers and network operators. So we are here for the people. So sort of talk about a report that we released in late October of last year, and not to read it verbatim, but just to go over the methodology, what this shows, and what MLab is useful for. Like I said, the large portion of our sites most of our sites are hosted within transit providers, so this starts to give us large perspectives. One of our tools, the NDT tool, the network diagnostic tool, which I'm sure that a lot of you guys know, is actually the version that connects to Measurement Lab is actually integrated into a number of clients that allow us a sort of pervasive measurement across the United States. So for example, we are the preferred measurement platform for the Greek regulators. We have been used for the SAMNOS platform in the United States. CIRA is working on this as well. So we have about 160,000 tests per day, coming from about 100,000 clients, 160,000, yeah. Coming from about 100 unique clients, basically every country across the world. As I said, what this gives us is, because we're in the transit providers, we can start to look at things like the interconnection performance between major access ISPs. And we can build a sort of a simple methodology based off of this location. So if we see, for example, that a user is having issues with their connectivity. We see, for example, rising round trip times, rising packet retransmissions or loss. If we see decreasing throughput, we can do a comparative methodology in order to start to isolate where potentially within the network path that this is occurring. So if we have access provider A, transit provider X, we can start to look, okay, so from A to another transit provider, Y, what does the performance look like? Does it change over time? Does it decrease? Do we see loss rates that we would not expect within a well-provisioned network? If we see that, okay, to this other transit provider that it seems to work fairly well, fairly stably, we can say, okay, then the problem isn't happening in the edge network itself of the access ISP. So this leaves us with two possible other choices, more or less. So we can take another segment of our population because we have a fair amount of tests, and we can say, okay, another access provider connecting to that first transit ISP X, what does that performance look like? If in this case we see fairly normal performance, then we start to say, okay, if it's not the access ISP, it's not the transit ISP, then maybe it's the interconnection. And as we take segments of the population and we take this over time and we take this across a large sample and we take this across other sites, then we start to say, okay, maybe there are interconnection issues, maybe there are provisioning issues going on here. And fortunately, at least in the United States, we do have a large enough sample. Every month we get, for example, for Comcast, about 62,000 tests. I think actually the numbers provided on this are lower than they actually are. But we start to get a lot of data from a diverse set of the locations in the United States. So this allows us to start matching the provisioning. And we recognize that bulk transfer test, for example, isn't a complete saturation of the pipe. So when I start to give numbers, I'm not claiming that this is the entirety of what people can push, but for a single threaded TCP connection that is trying to push as much data as quickly as possible, this is reflective. And I think that this is reflective of a large portion of how people use the internet, the applications that they're using. So we rely on baselines. That methodology was the assertion of different baselines. So we can say MLab had an interesting setup actually in New York, where we had a very good A-B scenario, as I showed you, where A was the transit provider Internet, and B was Cogent. And so, okay, we can say there is an interesting discussion going on in the United States currently in the public policy realm about the provisioning of interconnection and how that can be used in terms of business negotiations and other idiosyncrasies outside the technical realm. How does that baseline work? If we assume that, for example, Internet is not a primary vendor of some of the applications in dispute, how does their performance look like? And so in New York, we take the 4 access providers that we had the most amount of data for, which was Time Warner, Comcast, Verizon, and Cablevision. How does that performance look? Well, like any data, there's jitter, but there's consistency. There's a trend over time. And so we say, okay, this seems to be a fairly stable set of interconnections for a transit provider. Okay, so we assume then that Internet is fairly well provisioned. So let's take a baseline of access ISPs. Let's take an access ISP that has not been publicly accused of, or has not had public issues having to do with interconnection. Actually, in some cases, has an infrastructure setup that would avoid the problem. And so let's take Cablevision, and Cablevision to Cogent, our B site in this comparative. So what we see is stability, more or less. Again, jitter, some strange things, maybe a few research papers for the spikes, but nothing drastic. And I want to caution that in this, we're using the median. And so the median is subject to very extreme behavior when you're visualizing it. It's useful as an indicator, but it's important to take that into account. And if you see fluctuations, those fluctuations are bound to show in the data, you're bound to see actually a prelude to this sort of performance. So, okay. So this is Cablevision. So what we have left is we have Time Warner Cable, we have Comcast, and we have Verizon against Cogent. Okay, what do we see? Well, the differences are pretty stark. And as much as bulk throughput might have its problems, when you start to see basically 90% degradation over that median in the course of a month, something's going wrong. And when you see stability in the normal cases, and you start to see that basically within a month, the performance for this user population changes, all of a sudden that starts to tell you that there are underlying changes within the network. And so what we see is in the case of certain transit providers, that the access ISPs very quickly degrade in performance. And this is manifest across all of the parameters that one would generally expect. This is a decrease in throughput. This is an increase of loss. This is an increase of round trip time. They manifest differently, but what you see ultimately is a change in the throughput that is drastic. It is not subtle. We are not looking for subtle indicators like 40% change. We are looking at 80% change. And so, okay, this is one site. That might be a failure within a segment of a network that is shared. But what we see, in fact, MLab has about 4 sites at this time located in Cogent. What we see is very quickly across all Cogent sites, we start to see declining performance. They're rapid and they are more or less related. They aren't synchronous, but they are similar in nature. All of the access ISPs starting in spring of 2013 start to experience strong degradation of performance to Cogent in this case. These are AT&T, CenturyLink, Comcast, Time Warner, and Verizon. You might read about these issues in the news. So this is interesting behavior. But one of the things that's a little bit more illustrative is, okay, let's start to bin this within a month, put this within a month and bin it day over day. Well, what we see is exactly what we would expect. Within a well-provisioned network, more or less, you should see stability across time. There isn't a competition over resources. These factors sort of stay consistent. So we assume then when people are starting to compete over a fixed amount of resources that is not high enough to accommodate their user base, that we're going to see behavior like this, which is as people are loading up their over-the-top services when they get home at night, they are all trying to get through the same congested interconnection, and all of a sudden performance goes down for everyone because we share the same interconnection as all of these services. This is not obviously, as you know, it's not going to affect one particular service. It's going to affect everything behind that service. So incidentally, that's what MLab starts to see. So if we take the case that we showed before of interconnections with Cogent, what we see is similarly extreme. We see that in the early morning hours that you start to see median bandwidth or median throughput that vaguely resembles what you would expect out of cable or ADSL or Fios, especially across that median. But then all of a sudden when people start to wake up, this starts to degrade over time. And the lowest point is that 7 o'clock to 11 p.m. Hours that the FCC defines as on-peak hours. And when it gets low, it gets low. In the majority of these cases, it's actually less than half a meg compared to at night when it's in excess of 20 megs a second. So this isn't just download throughput, as I mentioned. You also see rising round trip times. This isn't just Cogent. You actually start to see this writ large across a number of the transit ISPs, and it might not even be connected with any particular service. It's maybe exacerbated by one, but this is something that we see across the landscape. And so, for example, when we take our user sample of EXO across Time Warner, we see the same behavior. We see that during the peak hours, all of a sudden the throughput is drastically different than what it is in off-peak hours. The lower portion, by the way, is our sampling population. So So what's really interesting about off-peak hours too is they start to augur that there are capacity constraints within the network. If you can see this, I think it's seen. The darker is the on-peak hours. The lighter at the top is the off-peak hours. And then the middle is what ends up being the median of the two. And so what we see is this consistently across time, that this sort of behavior that we saw here is repeated month over month. We also start to see towards the summer that all of a sudden there are resolutions within these capacity constraints. So again, not to pick on another, we see the same thing, level 3 in Verizon. In the case of level 3, what's interesting is that this is what we've seen as the most ongoing. We've seen the higher round trip times. We've seen the similar changes in throughput, anywhere from going down to less than what the broadband definition would be. And we also see at some point packet retransmission rates that are around 6%. So fairly high failures within the network. And these are also the median, and so this means that a lot of other people are 50th percentile are having worse performance than anything that I show you up here. Same sort of pattern. Degradation over time, remediation, the peak hours being a really good sense of something happening in the network. I'd also note that what our measurements are possibly showing in this case is a small remediation through possibly adding capacity in the point of interconnection. You see this across time, especially during the spring. We don't really say that it's, we don't make that claim within the paper, but I think that it is a likely hypothesis for why you see brief improvements of performance in the spring of 2013. And this continues. I can pull out some things. I think we'll do more blog posts on this, but just because one application has made different arrangements, we still see these diurnal changes in performance behavior that are experienced by real users and real samples of performance performed by the users. So just to belabor the point, what I want to show is our point is that this is not happening based off of the network of either the access ISP or the transit ISP. We're saying, okay, if there's a failure in New York and there's a failure in Los Angeles, the likelihood that there's a shared infrastructure that is causing this sort of behavior for as long as it is, it's likely not a technical issue. It's likely, a layer 8 or layer 9 problem that is causing technical manifestations. And so, if we bin all of our measurements together, these are put over different blocks of megs per second. But the eyeball test is, in any case, if on this you see more red than more red on the left-hand side, then that means that more measurements are coming in lower tiers. If you see lower on the left-hand side, then there's probably that's a better situation. That's a better and less congested relationship. So we can take this, and we can take these across within a grid of matching access ISPs and transit ISPs. And what we see is, okay, there is no transit ISP in this situation that is universally bad. There is at least 2 or so access ISPs that seem to have normal performance. So this is probably not happening within the transit ISP. There's probably no bad transit, a transit provider within our sample. So we can also take, okay, an access ISP, and we can do the same thing. We find situations in which the interconnection with particular transit providers are well performing. Of course, there's also ADSL, which unfortunately does not have a good go at it, which always looks bad in this slide. But the point being is that in this situation, we see that that it has to be happening at the points of interconnection between these particular relationships. So one of the other points that I wanted to bring home was that, by retaining all the data and publicly making it available, we start to find interesting additional things. You might have noticed that in that slide, you see a rapid increase of all of the access ISPs in coordination. That's strange because none of them there was no interconnection deal at that time for the majority of these arrangements. So something must have happened within this transit network. And we see it elsewhere. Rapid performance increase across all of the access ISPs. Well, by keeping all the PCAPs, which are again publicly available for anyone who wants it, by keeping all the PCAPs, we see all of a sudden that there is a change in the type of service flag. And so all of a sudden what had happened was that there was a prioritization scheme that was in effect, and by retaining all of this data, we were able to find a prioritization scheme that was not publicly disclosed. Now, this isn't the only way of doing traffic management. The BitTag report does a really good job of showing all the ways that you can use BGP and announcements to discriminate, but we start to get it at a much more intelligent view of the network based off of the data that we collect. And so, just to conclude, all of the tools, if you disagree with the methodology, with the findings, everything is available publicly. As I mentioned, all of our data is CC0. We've gone to the point of even taking the intermediate results, putting them up. The code in order to reproduce this is on GitHub. It's called Telescope. We have also launched the observatory, which tries to reproduce these in real time. That's available. The code for that is available. And to conclude, what we're able to do is at a third party start to show things that you'd only previously be able to see with MRTG graphs. And so this is interesting from a public policy standpoint because this starts to be comparative data that isn't reliant on a particular service provider or the argument of the person who holds the data, because this sort of information I think had been pretty well kept based off of non-disclosure agreements, based off of commercial interests. And this is the point of Measurement Lab, is to start to put transparency through the use of open measurement and collaborative projects. So with that, I should hope that there are questions and accusations. Seriously? Didn't I insult anyone? Okay. Thank you.